Okay, the subject of this video is what is the Einstein synchronization procedure? And moreover, I'm going to try to simplify the controversy because there is an equation in Einstein's paper, and this is the equation right here, t sub b minus t sub a equals t prime sub a minus t sub b. Let me go into detail about where that starts from, what that equation is doing. It says let a ray of light start at the a time t sub a from a towards b. Let it at the b time t sub b be reflected at b in the direction of a and arrive again at a in the a time t prime sub a. So let me draw a diagram of that. Space-time diagram. So time is vertical in this diagram, space is horizontal. So here's the position of clock A, here's the position of clock B. Here is the time t sub a, that is measured in the horizontal axis. Then we come over here and we have t sub b, and so the speed of the light travels from point A to point B and then back again, and it arrives back here at t sub a prime. And the difference between this time and this time is t sub b minus t sub a, and the difference between this time and this time is t sub a prime minus t sub b. Now, he says that the clocks synchronize if t sub b minus t sub a is equal to t prime sub a minus t sub b. Okay, but the question is, what have we actually said about the Einstein synchronization procedure? And have I fully described it? Basically, there were three things, or there was basically two parts of it. The first thing was obtain two clocks, and the second thing is t sub b minus t sub a is equal to t sub a prime minus t sub b. However, I think there's a couple of other criteria that we need to make sure of before we can actually declare that we have actually done the Einstein sync procedure. One of these things is we need to obtain, as well as two clocks, we need to obtain a ruler. We need to obtain a stationary ruler and put it here between the two clocks. And then we need to find a signal which has the same speed from the left to the right as it does from the right to the left. There's several different counterexamples I can come up with. For instance, let's think in terms of a sound wave, but we're not going to view the sound wave from the point of view of a stationary object in the air. We're gonna put the sound wave in an airplane. So here's our airplane, and you can imagine the speed of sound going from the back to the front is pretty slow. So I'll draw it like this, and then the speed of sound, or the speed of the sound wave going from front to back is pretty fast. So I haven't required that clock A or B is, you could describe this in one of two ways. This is clock A, this is clock B. One way to describe it is that A and B, clocks A and B are moving with respect to the air. Another way to describe it is that the signal is not isotropic. The signal going to the left is much faster than the speed of the signal going to the right. Now, it's possible to make this true, though. I can still make it so I can set the clock here. So here's what I'll do. I will set this clock to 0, and then I will set this clock to 1, and I will set this clock to 2. Well, I'm not setting this clock to 2. I'm just saying that if this clock is 2 here, then I better set this clock to 1 right here. So have I performed the Einstein synchronization procedure? I don't think I've successfully performed the synchronization procedure because this time it looks like it's more close to like 1.5. Am I going to say that because I see that this clock is set to the same, is not set to the same time as this clock over here. So I would not say that these two clocks, even though I have t sub b minus t sub a equals t sub a prime minus t sub a, I would say these clocks are not synchronized. Okay, so I'm making a little checklist, and as I'm making my checklist, I realize this should be t sub b. So what do we got? In this diagram here, do we have a stationary A and a stationary B? And do we have a stationary ruler? Our ruler in this case is basically the plane itself. The plane is moving with respect to the speed of the sound. But in our diagram here, the rulers are vertical straight lines. So we're going to say that in this case we have a stationary A, a stationary A, a stationary B, and a stationary ruler between them. It's compared to the ground, these things aren't stationary, but in the diagram I've drawn, they're stationary. Do we have an isotropic speed of sound? The speed of sound coming this way is quite slow, and then the speed of sound going this way is quite fast. So I'm going to say no on this one. We do not have an isotropic speed of sound. Do we have t sub b minus t sub a equals t sub a prime minus t sub b? We have t sub b minus t sub a is 1 minus 0. T sub a prime minus t sub b is 2 minus 1. So yes, we do have that. Would we say that these two clocks, would you say that these two clocks are synchronized? I would say not, because this clock seems to be reading minus 0.5 when this one reads 0. This one reads 1 at 1.5 and 1.5 at 2. I think, did I get that right? Yes, if things work logically speaking, it looks like this clock is just half a second behind this clock. So I would say no, they're not synchronized. So let's do this again with A, clocks A and B. Again, okay, my plane came out looking more like a whale this time, but again, we'll have the plane, but this time the speed of the plane will be moving with respect to the air. And so we will have the same slope, and I don't know exactly how to do this. Maybe a protractor? Okay, I've tried to make this somewhat close by using the protractor. This is a 20-degree angle, and then over here, well, I tried to make it a 20-degree angle too. Of course, without the straight line, how can you know whether it's 20 degrees? Okay, there's our in-between line. So we're going to come this way and figure out here is t sub a, here is t sub b, here is t sub a prime, and the things we're going to be comparing are t sub b minus t sub a, which seems to be a long time, while t sub a prime minus t sub b is a short time. Same phenomenon that we got in our situation here, but a little less drastic because of the angles I used and everything. But let's say here is 0. Here is, I think, looks like this is about 2/3 maybe, and this is 1. So what would this have to be? This would have to be set to 0.5. Okay, so again, let's go through our checklist. Okay, do we have a stationary ruler? No. Both elements of it are moving to the right. So say no. No? No, no. Isotropic signal? Is the speed of sound to the right the same as the speed of sound to the left? Yes. Is t sub b minus t sub a equal to t sub a prime minus t sub b? T sub a prime minus t sub b is 1 minus 0.5. That's going to be 0.5. T sub b minus t sub a, t sub b minus t sub a is 0.5. So we'll say yes on that one. Are the two clocks synchronized? No, because here this clock says 2/3 at the same time that this one says 0.5. So no, these two clocks are not synchronized. So the point of all this is that it is not enough to just obtain any two clocks and then set it so that t sub b is halfway between t sub a and t sub a prime. No. First, you have to obtain a stationary ruler. You have to obtain 2 points where a equals a prime, and really you need b equals b prime too. You need to have a ruler that's here and here at the same time, and if you don't have that stationary ruler, it's not going to work. And 2, you have to find an isotropic signal. In this case, the speed of light works as a isotropic signal because it's. But if you fail in either of those, if you don't have an isotropic speed of the signal, then you're not going to have synchronized clocks. And if you don't have a stationary ruler, you're not going to end up with synchronized clocks. Let's talk for a second about the symmetric property of an equivalence relation. An equivalence relation is basically anything that behaves like the equal sign in mathematics. And the equal sign, there's a symmetric property, a reflexive property, and a transitive property. Anything that the reflexive property is a thing is equal to itself. The symmetric property is if A equals B, then B equals A. And the transitive property is if A equals B and B equals C, then C equals A. But anyway, this is the idea of synchronization involves this symmetric property, meaning that if I say clock A is synchronizes with clock B, then it also should mean that clock B synchronizes with clock A. And the way we talk about the symmetric synchronization convention. Okay, so this synchronization principle that we've been describing is kind of a one-way. Notice that we had 2 clock readings over here, but only 1 clock reading over here. So I could have done, like, is that enough to say the 2 clocks are synchronous, just comparing these 2 events to this one event? I could have just made the trajectory of that other clock any direction I wanted, and just, it doesn't matter what the clock reads at any other time except that one. There's no comparison. So in order to actually say these things, this synchronization is symmetric, we have to go a little bit further, and that's what I'm trying to do here. To say that clock B is synchronous with clock A, you need to have a situation where A is equal to A prime, so the position of clock A stays the same, and some clock B, and it doesn't make a condition on clock B at this point. that it stays stationary. But you need to have these three events involved, that we have t sub a and t sub a prime compared to the time at clock b. And then these are the situation. T sub b minus t sub a is equal to AB over C is equal to BA prime over C. So here is the condition that really, this big condition is that A and A prime are the same, is kind of exposed in this part. And then equals T sub A prime minus T sub B is, this is sufficient to say that B synchronizes with A. And then to say that A synchronizes with B, we kind of go the opposite. A has an arbitrary motion, but B is equal to B prime, and so you have same thing except there's only one A term here and two B terms, and we're comparing T sub A minus T sub B to T sub B prime minus T sub A. Anyway, and we have to have those distances being the same. Now, this brings me to another question. In special relativity, who synchronizes the clocks? Now, I've been talking about sound waves, where you could use where, well, the person standing on the ground would observe this sort of motion, where both clocks A and B were moving, and the signal, the speed of sound was isotropic. Or you could have view it from aboard the airplane, where the clocks were stationary, but the speed of sound was not isotropic. So what if I were an observer watching, well, let's make it a rocket. I really shouldn't draw fire coming out the back because this rocket is not under acceleration, but we're imagining a light signal, or two clocks on the side of the rocket, and the light signal comes out, and in special relativity, even though the rocket's moving by, we're going to assume that the speed of light is isotropic with respect to us. And so this angle and this angle should be the same. So let's say I find out that this time is 0 and this time is 1. I'm supposed to synchronize these clocks according to that isotropic signal. And I go ahead and use Einstein's formula, T sub B minus T sub A equals T sub A prime minus T sub B. So what's that come out to? Well, it's halfway between 0 and 1, ends up being 0.5. Okay. However, I look over here, and this event corresponds to a time of, I don't know, 2/3. So, question: as this observer, because I'm watching this rocket go by, do I correct this? Do I change this 0.5 to a 2/3? Or do I just leave it 0.5? Well, as it happens, the person in the rocket actually put a 0.5 on it, and this equation actually puts a 0.5 on it times. Now, it's kind of a semantic issue, but my thing is I would not call this clock synchronous with this clock, even though it meets this equation here. It fails to meet the conditions of synchronization because, or as a result of, okay, it succeeds in having the isotropic signal, but it does not have the stationary ruler. So the clocks end up not being synchronized, and this is a matter of perspective. they're not synchronized from my point of view. They are synchronized from the rocket's point of view, but they're not synchronized from my point of view. So the synchronization procedure should consist of obtaining the clocks that tick at the same rate, measuring the distance between the clocks with a non-moving ruler, emitting the signals and making sure that those signals are isotropic by using that ruler, setting the clock, set t sub b equal t sub a plus ab over c when the signal from t sub a arrives. Then, if you look at that from a perspective with a velocity v, then the time t sub b minus t sub a in that new perspective is going to be r sub a over ab over c minus v, and t prime minus t sub b is equal to r sub ab over c plus v. Now, I think Einstein's derivation is weird, confusing, because he starts with this assumption that t sub b minus t sub a is equal to t sub a prime minus t sub b, and he derives that t sub b is this thing here. And then he concludes from this fact that the clocks were not synchronous. And when he says observers would thus find that the two clocks were not synchronous, his statement doesn't state mathematically how those observers find the two clocks were not synchronous, because he derived this fact that what t sub b was from assuming that t sub b minus t sub a was equal to t prime sub a minus t sub b. He derived it from his definition of synchronous. So it appears that he changed his definition of synchronous because he's like, okay, we just derived that the clocks were not synchronous from the fact, or from the assumption that the clocks were synchronous. But let's put it this way. We ought to always add the stipulation from whose point of view the clock seems synchronous. We derived that from the point of view of the person seeing the rocket move by, the clocks were not synchronous. We derived that they weren't synchronous from our point of view, from the assumptions that they were synchronous from the rocket's point of view.